Namaskar, welcome to this channel Chemistry Made Easy by Dr.ARM. We were discussing this molecular orbital theory, and in which we have seen last time in previous lectures the application of molecular orbital theory to the homonuclear diatomic molecules in terms of different points. Now we are going to see is heteronuclear diatomic molecules, means how this molecular orbital theory interprets the formation of such heteronuclear diatomic molecules. And the first point of this title is polar bonds. As we have seen in case of homonuclear diatomic molecules, there you can consider the simplest example of hydrogen bond, where the both atoms are of the same element, as a result of which there is no polarization. The electron density is concentrated between the two nuclei, which shows non-polar molecule, or the bond is called non-polar. The electron density is concentrated uniformly throughout the two nuclei. But in case of heteronuclear diatomic molecules, the molecule contains different atoms or atoms of different elements such as we can consider the carbon monoxide and HCl or any other molecule like this. Here you will find that instead of having two carbons or two oxygens in the molecule, it contains one atom of carbon and one atom of oxygen. So being the two atoms of different nature or different electron negativity values, these contribution of the electron density from both the atoms is different, or contribution of the atomic orbitals present in the valence shell of both the atoms is at different magnitude. So one atom will contribute less to that given molecular orbital and another atom will contribute less. So in this way the contribution is not equal to the molecular orbital as that we have seen in case of homonuclear diatomic molecules. So same the case will be observed in case of HCl. It is not seen in case of H2 or Cl2 molecule. Then we also come to understand that when we observe any of the element or any atom which is explained in the periodic table, starting from hydrogen to say the first period, that is hydrogen and helium, the second period has lithium to the neon, and again in case of third period. So in this way we can get the new element in every period, starting from first period, second period, third period, fourth period, in this way. So as we move from atomic elements with atomic number 1 to next element, what is our observation? The nuclear force of attraction increases gradually, and this nuclear force of attraction binds the valence electron strongly. The strength of binding the valence electron to the nucleus depends upon the nuclear charge present in the nucleus, and nuclear charge depends upon the atomic number, because the atomic number increases by an increase in the number of protons. So as there is increase in the number of protons in the nucleus, the nuclear charge increases, and increasing the nuclear charge binds the valence electron very or more and more strongly, and with increasing this strength of bonding with the nucleus, the electron shows different energies. These are called potential energy. So potential energies are considered here to represent the force or the strength of the electron that is bound with the nucleus. So in case of hydrogen, there is only one electron in the valence shell and one proton in the nucleus. So that electron is loosely bound, but still the electron is close to the nucleus or closest to the nucleus. The strength of the binding is also considerable, and it is minus 13.61. So this strength of the bond, or that is called this potential energy of valence electron, and it is explained in terms of electron volts, and it is in the negative terms. The value is negative, and using these negative values we can compare that how strongly the electrons, valence electrons, are bound to the nucleus of given atom of the element. So using these values we can compare with which atom or which element has the relatively stronger bonding, means the binding energy associated with the binding of nucleus to the nucleus. So we can compare these values in terms of electron volts. So this will explain how easy it is to detach that electron, and these values are also explaining about the energy of the associated atomic orbital. So we know that there are these such 1s atomic orbital, 2s atomic orbital, or 2p atomic orbitals, but we are having there such 3 orbitals involved in the p sub c. There is only one atomic orbital in this case, but we can place one electron in 1s, or we can place 2 electrons, and for both electrons of the same orbital the energies may be slightly different, but in order to avoid confusion we are averaging the potential, we are averaging this electrons, binding electrons or binding energy of the electrons to the nucleus. So because of this, the value of this energy level is same, unchanged. It remains unchanged for both the electrons. Similarly, we can have here 1 or 2 electrons. So when there are 2 electrons, the energy values, potential energy values are slightly different. But taking average of the values, we can say that there will be no confusion. We can understand how far is the distance between 1s and 2s. Similarly, we can have the 2p energy levels. We can place 1 to 6 electrons in these atomic orbitals. But every electron present in these values have different energy values. Every ionization energy, or we can say potential energy of each electron present in these 3 atomic orbitals is different. But for our convenience or avoid confusion, we are taking average of all these 6 electrons which can be accommodated in these values, in these atomic orbitals. So this will help us to understand the exact difference between the energy difference between the 2s and 2p. Means how far this 2p is placed from this 2s. So such types of terms are these states, means these are called states or terms, so which explain us the difference between the energies of the different energies of the 2 or more terms or states. So on this basis we can explain here, so what is the change. So in this topic we are going to cover the different points like this. We will understand the difference between energies of atomic orbitals of homonuclear, diatomic, homonuclear, heteronuclear atoms and the resulting molecular orbitals. Similarly, it will explain the trends in potential energies of valence shell or atoms with increasing nuclear charge. Similarly, it will explain why the contribution of atomic orbitals resulting atomic orbitals to resulting molecular orbitals is not equal. So we will discuss all these things one by one in this point. So first of all, we will see what are the values of these potential energies. So we show here potential energy values, potential energy values in electron volts for different elements. So for example, if we consider the first atom, that is element, that is hydrogen, so it has atomic number 1 and the orbital is 1s. The orbital is 1s and there is only one electron. So it has only one value of this energy. And what is this energy value? Minus 13.61. Now if we go to the next element, this is atomic number of element. Now if we consider the second element, that is helium, the atomic orbital is same. Atomic orbital is same. And we find that the nuclear charge increases. So being increased in the nuclear charge, the atomic orbital is same. What is the effect? This will bring the electron much closer to the nucleus of helium. As a result of which this value will be increased. There is increase in the value. And what is this? Minus 24.59 electron volts. So why there is increase in the potential energy? Because we are adding second electron in this atomic orbital. But there is also addition to the nuclear charge. So this will bring the electron closer, slightly closer, and it will require more energy. So it has more energy, potential energy. Now if we go to the next element, that is lithium, that is third. Thus valence shell, we are mentioning here only valence shells. We are not going to consider the inner orbitals. Now in case of lithium, we have 2s orbital. And it has the energy minus 5.39 electron volts. Now if we go to this 2s contains only one electron, that is third electron. Now in case of fourth, we are having the same atomic orbital 2s, but electron is increased and nuclear charge is also increased. So therefore the electrons are strongly bound. So in such case the potential energy must increase. So you will find that there is increase in the nuclear energy, that is minus 9.32 electron volt. Again if we go to the next element, carbon. So this carbon, this value, atomic number indicates that there is increase in the nuclear charge. But here the 2s is same. 2s is same. And in addition to this, there is 2p also. So with this 2s, the value of this electron, the two electrons which are present in the 2s are also increasing. So it becomes minus 14.05. 14.05. So you will observe that even though in this case, the two electrons are capable to complete this occupancy. So the capacity is completed. Here the electrons are also 2, so this orbital is also full, but there is increase in the energy. Why this is so? This is because of increasing the nuclear charge. In this case the nuclear charge is 4, here it is 5. So this increase in the nuclear charge increases the value of this potential energy. Then we are having the next orbital 2p. So the third electron of this carbon enters into this carbon, it is boron. So third electron of this boron enters into the 2p orbital and it has value of potential energy minus 8.30 electron. So this value is for that single electron present in 2p. Now if we go to the carbon with 6 electrons, means 6 nuclear charge, means the nuclear charge increases. The 2s remains the same, but electrons are also same. But because of increasing the nuclear charge, the all electrons are brought slightly closer. As a result of this, the energy also increases here. It becomes minus 19.43, and here 2p is same, but already there is one electron, and for this carbon we are adding one more electron, so that will also increase the energy of 2p. So the 2p value, or the potential energy value, also increases here. It becomes minus 10.66 electron volts. Then again, if we go to the next element, that is 7 nitrogen with 7 nuclear atomic number, that is nuclear charge. So here 2s is same. So compared to this, the energy is also increasing. In case of nitrogen, it becomes minus 25.56 electron, and there is also 2p with third electron, and compared to this, there must be increase in this value. So it becomes minus 13.18 electron volts. Again, so there is this progressive increase. Why it is so? Because of the increase in the nuclear charge. Then in case of 8th oxygen, the 2s remains same. 2s remains same, but there is increase in the nuclear charge, and therefore the potential energy of this 2s also increases, and it goes to minus 32.38 electron. There is also 2p with having one more electron. So this value is again increasing to minus 15.85 electron volts. So in this way, you will find there is progressive increase in the values as we move from one element to the other. So in this way, if we go to the 9, that is fluorine, the 2s remains same, but since there is increasing nuclear charge, this value, potential energy value for 2s electrons also increases, and it becomes minus 40.17 electron volts. For 2p electrons, the value again increases from 15.85 to 18.65 electron volts. And there is 10th atomic number for any where 2s is also there. The value again increases to minus 48.47. There is 2p having more value, that is having minus 21.59. So in this way, you will find a progressive increase in the every value because the period is same, means valence shell is same, but nuclear charge increases. So this is the effect of nuclear charge on the potential energy values of every element or every electron. So in this way, we can find we can have the number of such values. I will explain you here that if we go to the sodium, that is with 11. Now the third domain shell is open, that is 3s, and this has the value that is minus 5.14 electron volts. So if we compare this value of Na to lithium, so in case of lithium we have seen that the value, a potential energy value is minus 5.39, and in the same group the next element is sodium. So in case of lithium, the value was minus 5.39, and here it is minus 5.14. So here you will observe that in the same group, as we move down from top to bottom, the potential energy value decreases. Why there is so decrease? Because the new shell is added and the distance from nucleus and the valence shell is more, as a result of which the magnitude of potential energy decreases. But as we move from left to right in any period, you will find that there is continuous or progressive increase in the potential energy value of every electron. So similarly, I will read out these values here. So in case as we move from sodium to magnesium, the value must increase because we are adding the next electron in the same 3 s. So atomic orbital is same, but nuclear force is increased, nuclear charge is increased, so that the electron is brought closer and it will require the more amount of energy. So it becomes minus 7.65 for mg. So as we move to 13th element, that is aluminium. So aluminium has 3s as well as 3p. So the 3s value, potential energy value for 3s in aluminium also increases as compared to this magnesium, and it becomes minus 11.32. In case of 3p, the 3p is open. We are not considering the lower energies like 2p, etc. The 3p has minus 5.98. So in this way, as we keep on moving from aluminium, sodium to magnesium, magnesium to aluminium to silicon, etc., up to the argon, you will find that there is gradual increase in the potential energy values for these 3s valence shell as well as for this 3p. So here 2p is completed, the 3p is continued. So there will be continuous such increase in the or gradual increase in the potential energy values with increasing atomic number, but within the same period. But if we go down the group, there is decrease in the value because new shell is added. So in this way, in case of homonuclear diatomic molecules, we observe that another important thing is that so we have seen the comparison using these potential energy values. Now there is another important term which we are using in case of formation of the molecular orbitals using atomic orbitals. So when we are applying Schrodinger's wave theory, or we can in short we apply the LCO principle, linear combination of atomic orbitals. We are also making use of the terms such as C1, C2, that is, say for one atom, so we are saying this is X and this is Y atom. So this indicates the contribution of atomic orbital to the molecular orbital under consideration. So when this atom X has atomic orbital, say any atomic orbital, and it has comparable energy atomic orbital of this Y, then we show that the equation will have the C1, C2 terms, and depending upon the magnitude of contribution, actual contribution to the molecular orbital, the value or magnitude of this C1 and C2 will vary. It is not equal. In case of homonuclear diatomic molecules, the atoms are of same molecule element, therefore contribution is same, means C1 is equal to C2. But in case of heteronuclear diatomic molecules, say like carbon monoxide, we could consider the example of carbon monoxide. The carbon has less contribution to the bonding molecular orbitals, and oxygen shows more contribution to the bonding molecular orbitals. So the magnitude of this contribution to the resulting molecular orbital depends upon the electron negativity values of the LCO, linear combination of atomic orbitals participating in the formation of molecular orbitals. So the energies are also different because the distance between this nuclear charge is also different. So the contribution shows that how close these, say for example, the bonding molecular orbitals are close to the atomic orbitals of oxygen, whereas the atomic orbitals of carbon are found to be close to the antibonding molecular orbitals. So this closeness is dependent upon the electronegativity values of the participating atoms. So with this we will stop our discussion and we will discuss the actual examples in the next lecture in detail. So thank you very much for watching this video. Please subscribe to this channel and please press bell icon and like button also. So thank you very much.